Okay, so welcome to really the final lesson of the Unit 6 on similarity, because following this lesson there's no new content and we're going to be focusing on review for the unit test. So our focus today is on investigating a couple more cases of similarity, and that you should have done with your GSP, and I'm going to jump straight into that and then we'll address a little later on in the lesson an additional theorem relating to proportional lengths in overlapping triangles. Okay, and so what we did in a previous lesson is we established that we could show similarity between two triangles using the AA postulate, angle-angle. Of course, we know this combined with the theorem that says if two angles of one triangle are congruent to two angles in another, we know that the third is congruent. That guarantees us the same shape, and that, of course, gives us similarity. And so what your GSP exercise should have shown you was that we can also establish similarity of triangles using SAS, and so that of course must be a congruent angle. The angle must be contained between the two given sides, and those two sides must be proportional to two corresponding sides in the other triangle. Likewise, we can prove similarity by showing that all three pairs of corresponding sides are proportional, and so in other words that their ratios are equal. And the other important takeaway from your GSP is that side-side angle cannot be used to prove similarity. So there is an instance in which it holds, but there's also an instance in which it doesn't, and so we follow the premise we've been following all year in geometry, which is to say if it's not entirely true, it's false. And so we can see instances where SSA doesn't work, and therefore it does not hold as a theorem, as a way of proving triangles to be similar to each other. Likewise with congruency, but our focus is similarity. So what we're going to do is apply those three theorems in example 1 to determine if the given pairs of triangles are similar or not. And so of course when I'm talking about the given pairs of triangles, I'm talking about triangle CDE, and I'm talking about the larger triangle, triangle CAB. Okay, and so using the given information that we have on the diagram, we of course have angle C as a reflexive angle, and what we need to do is investigate whether the ratio of the sides then is proportional to determine if we have a side angle side similarity. And so what I'll do is I'll make a statement of CD over CE, and what I wish to determine is whether or not that is that ratio is equal to CA over CB. If so, we will have a side angle side similarity. Okay, so CD is 6 over CE is 8. On the right hand side we have CA, which of course we have to add 6 and 3 to get 9, and CB, 8 and 4 to give us 12, and both of those of course simplify to give us 3/4, and therefore we have established that we do have similarity by side angle side, and our similarity statement, one of the possible similarity statements, triangle CDE is similar to triangle CAB, and that's by side angle side, with angle C being the reflexive angle. Alright, if we go ahead and look at example 1b, this may look slightly familiar because we had some similar questions like this on the question press, only the difference here is you have been given the measure of an angle. And so if those two sides are equal and these two sides are equal, then they are naturally going to be in the same proportion. The ratio of KL over Kj is going to produce a ratio of 1, and likewise the ratio of GH to HI will also produce a ratio of 1 if they're congruent, and so we've already established corresponding sides are proportional, but the question is the angle included between them congruent or not for an SAS similarity proof. In this case we're going to use the ITBAB, the isosceles triangle theorem, if we know that angle L is 60. We of course know that angle J is 60, and then we know through angles of a triangle that therefore angle K is also 60, and this confirms for us that we have similarity by SAS. We also of course have similarity by AA. So either of those statements would be true, and in fact in this particular example we could also use the fact that we have 360-degree angles to also confirm the third side was congruent. Use the same logic in the other triangle. We could establish those are both 60 because of the angles of a triangle adding to 180 and those two being equal, and so we could likewise conclude that both of these triangles are equilateral triangles, and therefore that we also have side-side-side similarity. So in this case any one of the three could have been used. In this case, since I've made a proportional side statement, I'll follow on with angle K congruent to angle H, and therefore we have triangle L to K to J is similar to triangle G to H to I, and in this case by SAS, but like I mentioned, it could have been either of the other two cases based on the additional information I found from my diagram combined with the theorems from the first semester. Alright, and then if we look at example C, what we have here are no given angles and no common or reflexive angles, and so what we're going to need to do is establish ratio or proportion rather of all of the sides and see if they are congruent to each other. Okay, and so what I can do is look at the ratio. What I'll do is I'll establish for the small triangle over here, triangle GFH, I'm going to put smallest to the next smallest to the largest of the sides, and then I'm going to do the same thing in triangle FJI, and I'm going to go smallest, which is side FJ, to the medium side, which is JI, which is 10, and then of course I have FI, the third side, which is 12, and what I need to establish is whether or not those are equal to each other. 1/3 of course, 3/6 simplifies to 1/2, 6/12 simplifies to 1/2, but 4/10 of course simplifies to 2/5 or 0.4. Those are not all equal, and therefore the triangles are not similar to each other. Okay, so those are three examples of using the theorems to prove similarity. Of course, I didn't do a formal two-column proof, but I've more or less established all the key elements that we would need to do that. So if I go ahead to the second page, and what I'm going to do is I'm going to jump straight into example 3, the application problem, and then depending on how much time I have for this first portion of the video, then I'll either go back to example 2 or I'll leave that for the second part of the recording. Okay, so the application here, and I'll apologize in advance for my poor artwork. So we have a desire to estimate the height of the Marina Bay Sands Hotel and Casino. I'm measuring my shadow at 48 centimeters, and I'm estimating the tower's shadow to be 58 meters. So what I'll do is I'll start with a very poor rendition of the Marina Bay Sands Hotel and Casino, and I'll insert my sun over here, which of course is going to rather crudely help me cast the shadow, and that shadow will of course be cast on my ground, on the ground, and so what we've established so far is that I estimate the shadow of the tower to be 58 meters, and then my own shadow is at 48 centimeters, so I'm going to insert myself over here, and my shadow is being cast in this portion over here, and that is 48 centimeters. So the first thing to watch out for, of course, is that we have different units, and hopefully you remember from the first lesson that in order to establish or set up proportions or ratios, we need to make sure we're working in the same unit. And so 100 centimeters in a meter, I will change my shadow length to 0.48 meters in order to be consistent in terms of units of measurement. Okay, we're going to fill in the other information that we have, namely that I am 1.6 meters tall. Again, that's the unit that we're after, and what I'm looking to do is to estimate the height of the Marina Bay Sands. That's going to be my unknown. A couple of assumptions which you can make reasonably, or we will accept as fair assumptions. One is that we're going to have a 90-degree angle between the structure and the ground, and the other, maybe more risky assumption, that I'm standing at a 90-degree angle to the ground as well. What this allows us to do is to establish similarity between these two triangles, the small triangle of my shadow and my height to the shadow and the height of Marina Bay Sands by virtue of AA. So we each have a 90-degree angle and we have a reflexive angle over there. So we have AA similarity, which allows me to set up a proportion, and so I can say 0.48 divided by 1.6 is equal to, and so we've gone shadow on the ground to height equals shadow on the ground to height, and now we're going to solve for h by cross multiplying, and so if we take that over there and that over there, we're going to have 0.48h, which is going to be equal to 58 multiplied by 1.6, which is going to give us 92.8, and then of course we divide through by 48, sorry, not by 48, I beg your pardon, 92.8 divide through by 0.48, and we will have our estimated height of 193 1/3 meters for our height. Okay, and so that just shows you the application problem that uses, in this case, AA similarity of triangles. Okay, just a couple of minutes left, and so maybe just start off this example. What we're attempting to do is to establish whether or not, if we know that triangle x, x to y to q is similar to triangle x to z to p, whether or not that gives us sufficient information to determine whether triangle XPQ, and again it'll get a little messy here, XPQ, which is the small triangle at the top, is or is not going to be similar to X, Z, Y. And so what's important to establish here, of course, is whether or not we have enough information to establish similarity or not. Given the time limit, I'm going to stop right there. Take a look at it, see if you can establish that similarity or not, and I'll address that in the second part of the video.